All right. With temperature and velocity, we're going to eventually get to one major equation. U, the root mean square speed of a molecule, equals a square root of RT over the molar mass. And what we're going to show is the R here is a gas constant, so this is confusing. This is a gas constant, R, but it's a different gas constant numerically. It is the gas constant, but instead of units of liter atmospheres per mole Kelvin, it's in the SI units of joules per Kelvin mole. So this is another R you have to worry about. On an exam, you will see this equation, and this R will be given. Make sure you know which R to put into that equation. So let's go through this. When you're looking at molecules and molecular speeds, as we have shown, that at a temperature, at a given temperature, since all the kinetic energy, the average kinetic energy of the molecules must be the same, that means on average heavier molecules are moving more slowly than lighter molecules at that temperature. But note that's an average. What we see here is if you have O2 gas at 25 degrees Celsius, note that this is the curve. You've got the average speed, the top, close to the top of the curve is 25 degrees, represents 25 degrees Celsius. A certain, or the average speed here gives you that kinetic energy and that temperature. But you've got a range of speeds. Some molecules are moving slowly, some are moving much more quickly. But they average out to a certain kinetic energy, and that kinetic energy will give you 25 degrees Celsius. As you increase the temperature, note that this curve spreads out. You have a lot of molecules moving very slowly and a lot moving very, very, very quickly, but they average out, the speed averages out to give us a kinetic energy corresponding to 1000 degrees Celsius. So when we go through the math here, we're always going to be looking at the average speed of the molecules, not the speed of any individual molecule, because it might be going super fast or super slow. We're just going to be looking at the average speeds. Okay. But one thing, a nice number to realize, that most gases, in general, a regular old-fashioned medium weight gas moves at about, each molecule is moving on average 400 meters per second. That's about 1,000 miles per hour. That is the speed of the individual gas molecules on average as they are moving through space. So the air you're breathing, the oxygen gas you're breathing right now, very average molecule. Those oxygen molecules are moving a little over 400 meters per second, a little over 1,000 miles per hour as you're breathing them in and breathing them out. Okay. So let's do some math. You're not going to have to really derive it too much. You just need to know where these come from. Recall, kinetic energy is 1/2 mv squared. Instead of v for velocity, we're going to use u. M is the mass of the particle. The average kinetic energy, Ke with a line over it means average. Average kinetic energy equals 1/2 m average speed of the molecule squared. And this average speed of the molecule squared is called the mean squared speed. If that makes sense. It's the speed. It's the average, so it's the mean, and it's squared, the mean squared speed. Wow, that was easy. Experiments show that the average kinetic energy is equal to 3/2 RT. All right. Note R is our constant, 8.314 joules per Kelvin mole, these SI units. Which means this gives us that 1/2 mass times the mean squared speed is proportional to temperature. That's how we can relate these two. But who wants to know the square of the speed? If you want to know the speed itself, you have to square root it. So the square root of the mean squared speed, here the u squared with a line is the mean squared speed. The square root of the mean squared speed is called URMS, the root mean square. So the root mean square, this term here, equals a square root of 3RT divided by the molar mass. We're not going to discuss where that came from. If you want to know, ask Maxwell. Well, he's dead. You can't ask him. But you can look at his writings. And Maxwell's equation will show you this. With another little complication, the molar mass must be in kilograms per mole. Normally we think of molar mass in grams per mole. Now it's kilograms per mole. All right. So with this equation, then, we can do some calculations, some examples that show the different speeds of gases. Note that O2 gas is much heavier than helium gas, so right away we would assume that O2 gas is moving much faster than helium gas is at any, O2 gas is moving much slower than helium gas at any given temperature. The more massive, the slower it's going to go. And we can do the calculation. At 25 degrees Celsius, what is the root mean squared speed of O2 gas? Well, the root mean squared speed, plug it into here, is 3 times our gas constant times 298 times 32 times 10 to the negative third kilograms per mole. Remember, O2, you normally think, oh, that's 32 grams per mole. Yes, 32 grams per mole is 32 times 10 to the negative third kilograms per mole. And yes, that is not good scientific notation, but I just wanted to plug in this times 10 to the minus third to make everything easier. When you're converting grams per mole to kilograms per mole, whatever the molar mass is, just add a times 10 to the minus third after it, and then you've got it in kilograms per mole. Okay, now the units get a little hairy. My advice to you is don't worry about the units. When you work this part out, you get, since you have to take the cubed root here, or the square root of this, you get the square root of 2.32 times 10 to the 5th joules per kilogram. Yes, we gotta put in the square root there. 2.32 times 10 to the 5th joules per kilogram. Now, if we remember, which I never do, that 1 joule is 1 kilogram meter squared per second squared. Plug this into here, and then the units cancel out, and you literally get meters squared over second squared, because kilograms cancel out, and the square root of that is meters per second, 482 meters per second. So an oxygen O2 molecule at 25 degrees Celsius room temperature has a root mean square speed, kind of the average speed of an oxygen is 482 meters per second. Do the same calculation for helium, and you find it is 1,360 60 meters per second. Lighter molecules travel much, much more quickly. Okay. Moving on. Some other terms to be familiar with. Mean free path. Okay. That's just the distance a molecule can travel between collisions, because you've got all these molecules in here. They are moving very, very quickly, 400 some meters per second. They're going to smack into each other. The question is, how far can they get before they smack into another molecule? That is the mean free path. Note, at 298 Kelvin and 1 atmosphere, an N2 molecule travels on average 93 nanometers before it'll smack into something. And N2 is very small, so this 93 nanometer distance is really about 300 times the size. So an N2 molecule travels about 300 times its own length at about 400 meters per second, about 1,000 miles per hour, before it'll smack into they'll go about 300 times its own length before it'll smack into another molecule. Note, if you lower pressure, there are various ways to lower pressure: increase the volume, take out some gas and lower less moles of the gas. The lower the pressure, the fewer the molecules in there to run into, the less the density of those molecules, the larger the mean free path. Note, your book has a pretty decent diagram here of the mean free path of a molecule. We'll do a little shaking up here. And here it is. So when you have an atom in here, a molecule is just zipping all over the place, and when it hits something else, remember these are elastic collisions, no energy loss, no attraction, and it's just zipping all over the place like that. All right. And so this gives us two other terms that are related to this mean free path. It's related to this molecule just kind of bouncing randomly all over the place. And those two terms are diffusion and effusion. Okay, we'll come back to this book. Diffusion. Note, the collisions of gas molecules are colliding at different speeds. So if you were to release a gas in one corner of a container, due to diffusion, due to the fact that these molecules are randomly smacking into other molecules and moving all over the place, the molecules of the gas you release will diffuse, will interact with the other molecules and spread out over the entire room. And molecules always diffuse from a higher concentration to the lower concentration. So if you were in one corner of your room making a really good pasta sauce, people at the other end of the room will eventually smell that pasta sauce because that smell will diffuse throughout the room. Note, the heavier the molecule it is, the slower its speed, the less quickly it will diffuse to the other end of the room. All right. There's also effusion, gas escaping into a lower pressure container through a small hole. And your book had that diagram too, right here, where on the left side you have a lot of gas molecules in that container, and on the right side there's just a couple gas molecules because there's a little hole that they are effusing through. And Graham looked at this. Fun fact, you know graham crackers? In this Graham, not related whatsoever. Okay, but Graham looked at that, and what Graham found here, where are you? What Graham found was that the rate of any gas A effusing through that hole divided by the rate of gas B effusing through that hole is equal to the square root of the molar mass of B divided by the molar mass of A. What this allows us to do is we can just make these chambers, make two chambers separated by a barrier that has a small hole in it. Then take a gas that you know, what it is, put it in the one chamber, block the hole, put that gas in one side of the chamber, get a pump to pump out all the gas from the other side so it's a vacuum, then unblock that hole, let that gas effuse to the other side and calculate the rate, wait a certain amount of time. We'll see how long you have to wait until the two sides have the same pressure, and then you've got the rate of effusion. And then if you have a gas where you have no idea what it is, you've just done the experiment with the gas where you know what it is, so you know its molar mass. You have a gas you have no idea what its molar mass is, you have no idea what the gas is. Put it in the same containers, do the same experiment, and then you get the rate of that second gas effusing. You know the rate of that second gas effusing. If you know the rate of the first gas, the rate of the second gas that you don't know, you know the molar mass of the first gas, then you can calculate the molar mass of that second gas. So just by doing that, you can now get the molar mass of a gas. And yes, this is not a typo. The rate of A divided by the rate of B equals the square root of the molar mass of B divided by the molar mass of A. A over B on the one side, B over A on the other side. Okay. And now we come to just a nice little fun fact, almost as if you're going to feel like you were tricked, but that's not the case. Remember the ideal gas law? Everyone loves the ideal gas law, PV equals nRT. There is a problem with PV equals nRT. It is only for an ideal gas, and for a gas to be truly ideal, a true ideal gas would mean two things. First thing, not too controversial, is that the molecules do not attract or repel each other. Remember, all the collisions have to be elastic, no attractions or repulsions. The truth is that's not the case. All molecules kind of attract each other a little bit. At some distance, there's a bit of an attraction between two molecules. The next chapter, we're going to look at intermolecular forces, and if your gas is polar, hey, remember last chapter when we're looking at is a molecule polar or not? Well, if our gas is polar, then those gas molecules are fairly well attracted to each other, which means due to these types of attractions, there's no such thing as a collision that is purely elastic. The other problem is that for an ideal gas, the volume of the gas molecules themselves has to be zero. The gas molecules themselves can occupy no volume. 100% of the volume of the gas must be the space in between the molecules. What does this mean? Well, it means there's no such thing as an ideal gas. Here's a law for something that doesn't exist. No such thing as an ideal gas. However, recall that even though molecules, all the collisions are not totally elastic, the amount of attraction for most gases is very small. O2 gas, N2 gas, helium gas especially, the attraction between those molecules is extremely, extremely tiny. So we don't worry about it. And the other aspect of it, the volume of the gas molecules themselves, well, recall the volume of argon gas is 0.01% the volume of the gas. Of the volume of the gas itself. So the molecules themselves, their volume is very, very tiny for the most part compared to the volume of the gas, so we don't worry about it either. What this means is the ideal gas law for most gases works just fine. It works out really well. So we always use the ideal gas law. It works well. You use our ideal gas law, you're going to get a value to usually within 1% of the real value in terms of your error or something like that. So it's really, really good for most gases. However, we need to know that for some gases it really breaks down. Superpolar gases it breaks down. Very large gases it can break down. And for that we have the van der Waals equation, where we've got some shrubbery in here. If we get rid of this, that's just P. We get rid of this, and that's just V. So this is PV equals nRT. But we're going to modify the pressure because of the intermolecular forces, because of attractions and repulsions between molecules. And because the volume of the gas, there is a little bit of, the molecules themselves have a little bit of volume, we're going to subtract from the volume of the gas the volume of the molecules. Now, A and B, these two things can be looked up in tables, and the fact of the matter is we're not going to deal with it. From the van der Waals equation, all I really want you to get out of this is it does exist. There's really no such thing as an ideal gas. However, most gases behave ideally. To 3 sig figs, maybe 4 significant figures, most gases are ideal. When that's not the case, when you have gases that just don't want to behave ideally, we do have the van der Waals equation that will account for that. I will tell you this, I did not do a whole lot of gas chemistry in my research, but whenever I did, we used ideal gas law and didn't worry about it. All right, that is it for the gases chapter.